So yeah, regardless, inshallah, we are still in good spirit, and stay safe, stay healthy, and also if you have any concern, just let me know. Yeah, especially regarding this course that has to be conducted online. Okay, using this what we call as RTL, remote teaching and learning approach. Right. Okay. I'm hoping that we can finish the first lesson today. Yeah. So let's have a look. I'm going to share with you my screen. Yes. Let's see. Okay, can you now see my screen? The other one, the one with the slides.
Can.
You can, yeah? Okay, okay, good. Okay, so I think we got up to, let's see. Okay, this example last time. Look at it for one time. I think the slide is quite that question. Okay,
Sir, your mic didn't open, sir.
okay, that's how is it?
Okay.
Okay.
Yes, sir.
Okay. Sorry, I don't know what happened. And just a minute, let me get my pen so that I can draw on my my screen. Okay, please remind me again in case the mic stops working again, because I've got two screens in front of me and I don't monitor the one that shows the condition or the Google Meet window. Okay, right. So where are we? Where's the screen again? Right. Okay, I think the microphone is still okay, yeah? Okay, so okay, let me repeat. So the Faraday's law states that if a flux passes through a turn of coil of wire, yeah, you can see the illustration here. Just this color, yeah, this coil. Yeah, a flux passes through a turn of coil of wire. A voltage will be induced in the turn of wire that is directly proportional to the rate of change in the flux with respect to time. Yeah. So yeah, as I said, what we need to underline here is the rate of change in the flux. Okay, which is a d flux by dt. So there has to be a change in the flux. If the flux is constant, then you will not get this induction of voltage. Yeah? The voltage will not be induced. Okay, and yeah, the equation for this law is induced voltage equals to minus n d flux by dt. The magnitude of the induced voltage is simply n d flux by dt. This minus or negative sign is due to the expression of Lenz's law. Yeah? You can see at the bottom here below that it's basically to tell us the polarity of the voltage. The polarity of the voltage that will be induced. The voltage will induce another magnetic field. So the magnetic field induced by the voltage will be in the opposite direction to the primary or the first magnetic field that induced the voltage. Okay, so you have two processes here. So you've got the flux by dt. This will induce voltage. Yeah. But the voltage will also induce another magnetic field. And this magnetic field also will change with time. So it's got d flux by dt, right? And this is in the opposite direction to the first one. So there is a polarity of the induced voltage. And the polarity of the induced voltage is defined by this Lenz's law. Okay. However, for us, the main thing is the magnitude, which is n d flux by dt, and d flux by dt. N is again, what is it? N?
It's the number of turns around the coil.
Yes, number of turns. Coil. Yeah, correct. Yes, it's the number of turns in the coil. Yeah. And then d flux by dt is the rate of change of. And that's why in this, unfortunately, on this OneNote, I cannot run the animation. Yeah, but basically this, you have to move this, keep moving the what they call the magnet bar closer, and then move it further away and closer again to the coil. Yeah, so it's you move it in these directions. Yeah? If it is stationary like this, yeah, then you will not see any output. The output will just be 0 volt registered by the voltmeter. Yeah. Okay, but if you move it closer and then further away, then voltage will be induced in the in changing polarity depending on the direction of the motion of the magnet bar. Okay, right. So now if you look at the last point here on the slide, that Faraday's law is the fundamental property of magnetic field involved in transformer operation. Right. Okay. Here specifically we are talking about the secondary winding of the transformer, not the primary winding. Okay. When we look at transformer later on, maybe we don't do it in this semester, but let's see. You've got primary, but I'm sure you have seen a transformer before. I mean, you have learned about transformer, some basic introduction to transformer. So you got primary and secondary. So you apply AC current here. Yeah, apply AC. And then if you measure it, then you can measure the voltage and AC as well. So this Faraday's law actually referring to the secondary, yeah, not the primary, yeah, which is the induction of voltage. Induction of voltage is happening on the secondary. On the primary, what you get is induction of magnetic field. Yeah, you apply currents, electrical currents to the coil, the primary coil, then magnetic field will be induced. Okay, but again, this Faraday's law specifically referring to the effects happening on the secondary winding of the transformer. Yeah. Right. Okay. Now, you can just give me a shout if you want to ask any question. You can stop me anytime. Right. For the next one, the second effect is the production of induced force on a wire, which is a basic principle of a motor. Yeah. The second major effect of a magnetic field on its surrounding is that it induces a force. Yeah, induces a force on a current carrying wire within the field. Okay, and here we've got this. This is the piece of wire, and currently its location or position inside a magnetic field. Yeah, magnetic field B, and it's represented by all these X. Yeah. This X representing the direction of the vector of the magnetic field. Can you tell me what is the direction of the magnetic field? Is it going into the page or out of the page with the X? What is the notation X mean? What does it mean? Anyone?
Can you repeat that again, sir? The question, what is it?
Okay, the notations X, yeah, it's like a crosses here. Can you see it? All these crosses.
Yes.
Yeah, can you see? This is to represent the vector B, and it gives you the direction actually. So what is the direction of the B based on the common understanding of how this notation is used? X.
Going out of the paper.
Out of the
Going
page.
out of the paper. Yeah.
All right. Okay. So it means it's coming towards you. Yeah.
Yes.
Okay. Any other opinion? Everybody agrees with that?
Yes.
You agree? Okay. What is the other symbol that is used instead of X in addition to X?
A dot.
Yeah, it's a dot. Actually, it's a dot. Yeah. Do you know what do they signify? These two, cross and dot.
The direction of the
cross
will help you. If you
is-
understand it, then it will help you to understand, to remember. Yeah, to remember, not to get mixed up. Which is which? What do they
The
signify?
cross is again dotted. Signifies that the field is coming towards out of the way
Yeah, I mean,
towards us.
where do they come from? These two symbols.
A vector?
Where do they come?
Yes, it's a vector. Yes, it's to signify a vector. But why we use this? We use this. If you remember, I mean, it comes from an arrow, yeah. An arrow with 4 fins, if you like. This is the fins. Yeah, you can, but there are 4 of them. So if you look at the arrow. Yeah, if you look at the arrow, if you look at from this side, if you have 4 fins, yeah, then it will look like what? Look like a cross. Yeah, but if you look at from this end, I mean, yeah, you might still look at you can still see the cross, but the closest to you will be this point here. Yeah, this point. So it will look like a dot, Okay. Can you follow this? Yeah. So dot represents that it's coming towards you. Yeah, I mean the arrow normally goes in the direction, right? So a dot means it's coming towards you. Okay, so it means that it's coming out of the page, or out of the paper, or out of the whatever. Yeah, but with the cross, it's if you are from this side, this is your why is it so thick? This. Okay, try again. Yeah, so if you look from this side, then the arrow will be flying away from you, right? It's going this direction. So when you see cross, it means that it's going away from you, which means that it's going onto the page or the paper or the wall or the whiteboard or whatever. Yeah. So it's going away from you. So hopefully, if you understand this, then you don't get mixed up. Okay. So the crosses that we have on this illustration means that the B or the magnetic field is going into the page. Yeah. So away from you. Okay, is that already? Okay, now so you've got this magnetic field, and then you've got this coil. This wire, piece of wire. Yeah. Then what happens? In the wire, yeah, current is flowing. Yeah, you got this current is flowing downwards. Okay. So then, because you've got magnetic field, and then you've got this current in the magnetic field with current flowing in the wire, then a force will be induced. A force will be induced. This is the force. Okay. Yeah, and the force will be induced. Now the question is then which direction the force will be. Okay. Before we answer that, let's go back to the text first to find or to look at the equation. Yeah. To calculate the force that is induced, we use this equation that F is equal to I times in brackets L cross B. Yeah. L is the length of the wire, and B is the magnetic field density, and I is the current. Okay. Right. And so the next equation is, this is the vector. It will give you the vector, including the direction, but the magnitude itself of the force, the magnitude of the force will be given by this. Yeah? ILB sine theta, where theta is the angle between the wire and the flux density vector. Okay, so theta is the angle between L and B. Right. Okay. Now, so the direction of the force is given by the Fleming's left-hand rule. So you need to use your let's see if I can show it on the screen. Left hand. Is it seen as left hand on your screen? Because sometimes the camera will flip it over. This is left hand. Yeah? This is my left hand.
Yes, yes.
Okay, good. Yeah. So you've got FBI. Yeah? Just remember all this American agent, yeah? FBI. So F is we start from the top, then down and down. So FBI. Thumb is F, and the point finger is B, and the middle finger is I. Yeah, representing I. What is F? F is the force. B is the magnetic field density, and I is the current. Okay, the direction of current. Right. Okay. So please remember, we use the left hand when we talk about induction of force. Yeah. Because later we have induction of voltage, and then we have to use the right hand. This is for the left hand side. Is we use it when we talk about induction of force, and induction of force is happening if you have B and I. Yeah. So you got B and I, then you will have induction of force. This force will be induced. Okay. Right. So if you look at the screen again, the slide, yeah, the B is pointing away from you into the page. So this is B pointing towards the page, yeah, away from me. So going in that direction, and I is downward. So I is downward, and therefore F is going to the right hand side. Yeah, this is signifies or represents the direction of the force. So F is to the right hand side, yeah, which is in agreement with the illustration that you have on the slide. Yeah? So F is towards the right hand side. Okay, so that's how you use the Fleming's left hand rule. And again, please remember that you use the left hand when you talk about induction of force, and also when we talk about motors, yeah, because motor is we are talking about induction of force, and this force will be transformed into torque. Yeah. Okay, so don't get mixed up. If you use your right hand, then you'll get the wrong answer. Yeah, the direction will be the opposite. Okay, now right. So for this one here, okay, you've got a piece of wire in a magnetic field B, yeah, and then it's got a length of L, and a current is flowing in the wire in the upward direction. So to find the direction again, we use the left hand, B and I. So B is again still away from us, away from me, and then I is upward. So F should be in the towards the right, towards the left hand side. Yeah? So F will be towards the left hand side. And then what about the magnitude? The magnitude, you use this equation here. F it's slow, my laptop today. Okay. Oh, sorry. I think I'm using two monitors, that's why it's make it slow. Okay, F equals to L sine theta. Okay. Right. So, but theta is 90 degrees here. Yeah. Theta is the angle between L and B. Between L and B. So L is this direction, yeah, vertical, and B is into the plate. So the angle between these two is 90 degree. So sin 90 degree is 1, yeah. So this is equal to 1 times 1. So just B times I times L. So the B is this, I is 0.5, and L is 1. So just multiply all these numbers together. 0.25 times 1 times 0.5. So equal to 0.125 Newton. Okay. And it's to the left hand side. Okay, so it's to the left. Right, I think it's quite straightforward. It's just one tricky thing is in using the right hand. Is it left or right? Okay, now the next the basic principles of a generator. Remember, the generator is generators to convert from mechanical to voltage. So the output is voltage electrical energy, which is represented in voltage. Right. So the third measure in which a magnetic field interacts with its surrounding is that if a wire with the proper orientation moves through a magnetic field, a voltage is induced in it. Okay. So what do you have in here? Right. So you still have the magnetic field. You've got still a magnetic field. And then you've got a wire with the proper orientation, and it moves. So it's not stationary. It has to be moving through a magnetic field. Yeah, magnetic again. You can delete the first one. Okay. Then a voltage will be induced. Yeah. Right. So, and again here, what we need to highlight is the wire has to be moving. If the wire is stationary, then you will not get the voltage as induced in the wire. Okay. Right. And then that's why in generator that the wire is actually wound on the rotor. Yeah. And the rotor has to be moving. Yeah. For example, like if you have a wind turbine, then there has to be wind. Wind has to be flowing, and then this will cause the blades to turn around. Yeah. And inside the turbine, the rotor will be moving. If there's no wind, the blades are stationary. Yeah. So the rotor will be stationary as well, and there's no voltage output that you can get. Okay, so the thing here that we need to highlight is that the wire has to be moving in the magnetic field, right? And then the voltage induced in the wire is given by this equation in brackets V cross B times dot product with L, which is the length of the wire. And we have a new quantity here that has not been shown before, which is V. V is the speed of the wire. Okay, it's the velocity of the wire with respect to B. Yeah, which is B is the magnetic flux density. So it has to be moving relative to the magnetic field. Yeah, and you can achieve this in different ways. Yeah, you can move the wire inside the magnetic field, or if the wire is stationary, you can move the magnetic field. So you can achieve it into different ways. Yeah? Either you move the wire, or you move the magnetic field somehow. Somehow you move the magnetic field. Okay, right. So right, and then the equation can be, I think, you just use what we learned from a vector calculation. Then the magnitude of this, yeah, will be given by this. Why the alpha is the angle between the vector that you generate from this operation. Yeah, v cross b will give you another vector. Yeah. So alpha is the angle between that vector and L, and then theta is the angle between V and B. Okay. Right. Okay. The voltage in the wire will be built so that the positive end is in the direction of the vector V cross B. Okay, and then you can also use the what we call the Fleming's right-hand rule. So if you use FBI again, but now use your right-hand side hand, yeah, your right hand. V F is the actual symbol is actually V, but V and F is like the same thing, yeah. But the F, why we use F, because just for us to be easily remember, because it will be the same as the previous one. So, but this F is actually V now, yeah, which is the speed. So you got V, BI, VBI. So V is to the right hand side, and B is what do you call into the page. So I is a bit awkward. I is going upwards. Yeah. So in this, yeah, the V is to the right hand side. If you look at the illustration, it's to the right. I cannot draw. Yeah, it's very, very slow. Let's see if I can close. So maybe. Okay, so the V is to the right hand side. It's not responding to something to do with my pen, or is it the processing is a bit too much? I cannot use my pen now. Okay, but yeah, if you look at the illustration again, the wire and the magnetic field, you can see here V to the right hand side. Yeah, so again, if we do this, V is the thumb, is toward the right hand side, and B away from me. Yeah, this is B away from me, and I is pointing upwards. Yeah. So the direction of I inside the wire in this case will be going up. But if you look in this voltage, yeah, the polarity. If you got a battery and then you draw a, it's not very nice without the pen. Yeah. Okay, got it back. Okay, if I draw a battery, yeah. Okay, I can use the symbol, but not for now. I just draw the battery, right? And then you somehow connect piece of wire with some resistor, right? The polarity of the battery, this will be positive, this is negative. Okay. the current, can you tell me the direction of the current? Is it clockwise or anti-clockwise? Are you still with me?
Yes, sir.
The direction of current, is it clockwise or anti-clockwise? Okay. Yes. So which direction is the current?
Do you mean the one that you just draw?
Yes, here. In this
Ping up.
closed loop circuit.
Clockwise.
Clockwise. Why clockwise?
Positive to negative.
The current always flow from high potential to low.
Your voice is very very low.
Because the current always flows from the high potential to low potential, so from positive to negative.
Okay, yeah. Okay, thank you. So yeah, by convention, it goes from the high potential or the positive to the negative. Yeah, in this case. So current will flow in this direction, which is clockwise. Yeah? Right. Although in reality, what is moving is the electron, and the electron actually moving in this direction, the opposite. But by convention, so that we just follow that the current flows from the high potential to the low potential. Yeah, so from positive to negative. Right. Okay, so that's correct. However, in this, if let's go back to the, if we go back to the our case here, the induction. Just wait for a bit. Not responding again. Okay, the current is flowing upward. Yeah. But if you look the polarity of the induced voltage, negative is down here, positive is down up there. So what's happening here? So it's from the negative to the positive. Yeah. Is it true or is it something wrong or is it just there's an explanation behind it? Yeah. Okay. The explanation is actually what we have. This induction of voltage is like the production of voltage. Okay. Why my screen, my laptop is moving on its own? Okay, so if you look at the illustration with the battery with and the closed loop again. If you look at inside the battery, current flows from bottom to the top, which is from negative to positive. Okay, outside the battery, yes, it goes from the high potential to the low one, but inside the battery actually is the other way around. So similarly, in our case, our induction is just like the generation of the voltage, just like the battery chemically generate the voltage. The voltage is different. So similarly, this is like inside. But when if you then connect this wire to a component outside, then you will see that the current actually flowing similarly, just like in the battery case, is from the high potential to the low potential. Okay, so this is just something for us to underline that the polarity is still positive at the top and negative at the bottom, but the current flows upward, yeah? Because this is where the voltage difference is being generated. Okay, and example 1.8, I think is quite straightforward. It's nothing tricky in there. And then again, for the direction, you can use skip it for now. You can have a look. at it at your own time. If you have any questions, just let me know. Okay, again, this slide shows us the summary of the left hand and the right hand rules. Yeah, left hand is for motor and right hand for generator. Okay, and then right hand is induction of voltage, while the left hand is the induction of force. Okay, so don't get mixed up, and both of them use, you can simplify, you can say that this FBI. Similarly here, F, although the actual case is V, and then BI, so just for us to remember easier, more easily. Okay. Any question up to here? This title is slightly wrong. This is supposed to be like energy losses in a ferromagnetic core, not electromagnetic core. But if you don't have any question, let's. What time is it now? Okay. Right. A few slides on the losses in ferromagnetic core. So there are two types of losses here that we are going to discuss on this topic. The first one is hysteresis losses, and the second one later on it will be eddy current losses. So what is hysteresis losses? And both of these losses are happening inside the core. Yeah? So it's not happening in the coil, for example, but both of these losses are happening inside the ferromagnetic core. Okay, the first one, hysteresis losses, is something to do with the magnetic effect, while the second one, eddy current, is more on the electrical effect, if you like, although it's also caused by the magnetic field. Right, so the first one, hysteresis losses. So what is hysteresis losses? Right, if you have again, you've got a ferromagnetic core. Then you wind again a coil, just like what we had before. Then you start to apply current to the coil. Yeah. You apply current to the coil, just like this. Yeah, it's an AC current. So you start from zero, and then it goes up. Yeah, keep increasing until it reaches the peak, and then start decreasing, going through zero, and then negative. Yeah, the opposite polarity, and then it reaches the minimum, and then turns direction going up again. So, and then it will repeat itself periodically. So it's an AC current signal driven into the coil. So what will happen? Remember that magnetic field will be induced, actually direction fluctuating. So if you look at the plot, here, so as the current is increasing, yeah, this current is increasing, MMF, yeah, which is this, the curly F, is also increasing, because MMF is simply N times I. So as the I is increasing, the MMF is increasing. So we start from I equal to 0, then we start from this 0 coordinate. So as the F is increasing, the flux, yeah, on the y-axis is also increasing. This is the induced flux. Yes, so we will follow this path here. Okay, until the current reaches the point, the peak here. Then the current will start decreasing. But when it's decreasing, the path that we are going to plot, if we keep recording the flux, yeah, if we keep measuring the flux, it will follow a different path. It's not going to be exactly the same path. So we'll follow this path. okay, and so on. Yeah, as it's decreasing, then when the I is increasing again after it reaches the trough here, yeah, the minimum point, then it will follow this path. Okay, so there is a difference between the path when the current is increasing and the path when the current is decreasing, and this is what we call as the hysteresis. Yeah? The difference in the path when the input is going in one direction to the path of the output when the input is going the opposite direction. So this is what we call as, again, hysteresis. And hysteresis effect is not only happening in this magnetic field, but also happening in other physical or what we call physical domains as well. Yeah. Right. Okay. So yes, and this hysteresis, the difference of paths means that there is an area in the middle here between the two paths, and the larger the area, actually, the larger the losses, the hysteresis losses. Yeah. Why? Because it means that to be able, for example, yeah, if you this C, this point C, yeah, if I just let me clean it up first. Okay, you look at again here. There's a point here, but we call as residual flux. Yeah. So even if the current is already zero, there is some residual flux in the core, which means now the core has become magnetized. Yeah, it will retain some flux, although you have removed the current. Yeah, if there is zero current, because the core has been magnetized, it will retain some flux in it. Okay, and to make this flux zero again, you have to apply current, negative, yeah, in the opposite direction, and then it will follow this path, and the current or the flux will become zero again. So it means that to make it zero flux, now you have to apply current, which means that you have to input some energy into the coil, okay, and so on. It will follow. Okay. Now it means that now you need to use some energy to some energy will be used in this process. Okay, and this is why we've got this hysteresis losses, because some of the energy actually used by the or absorbed by the ferromagnetic core. Why? The reason is because this hysteresis. And why is this hysteresis? We can see it on the next slide. Yeah? Why we got this hysteresis? Yes, this hysteresis losses because of when we look into the atomic level of the material of the core, then we've got this magnetic subdomains, if you like, yeah? Magnetic domains, small magnetic domains. Yeah, if we don't apply any magnetic field into it, you've got this situation here, yeah, where the magnetic domains are oriented, yeah, or pointing in the different direction randomly. And because they're pointing in different direction randomly, the net magnetic field is zero. Yeah, because all these are vectors and they are pointing randomly, and then normally the net magnetic field will be close to zero at least, yeah, or zero. But when you then apply some magnetic field, then the magnetic domains becomes line up together in the same direction following the applied magnetic field. And here it becomes magnetized and the magnetic field is no longer zero. Okay, so and then when you apply the magnetic field in the opposite direction, this will then go into the opposite direction. Right. So the orientation of these magnetic domains apparently needs energy. Yeah, it needs energy, and that's why when we apply this AC current into the coil, sorry, and it will then have this hysteresis losses because of the reorientation of these magnetic domains inside the core. Yeah. Right. Okay. So again, this losses is associated with the magnetic domains, which is due to the magnetic effect that we apply, that is actually applied to the core. Yeah. Right. So this is the first type of losses, and the second type of losses we call this eddy current loss. Yeah, eddy current losses. Yeah. Again, this is also happening inside the core, but happening in a different way. And the total or the sum of these two losses are called as the core losses, which is the hysteresis loss plus the eddy current loss. And how this eddy current loss happening? Right, it's just the same manner as it would in a wire wrapped around the core. Okay, remember that if you have a coil and then you've got a magnetic field, yeah, that is changing with time, then you get induced voltage in the coil. Okay, but when we've got the ferromagnetic core, yeah, you got ferromagnetic core in the middle. This ferromagnetic core is also conductive. Yeah, it's conductive. Conductive means that electrical current, can flow through the core as well. Yeah. So the effect that happening to the coil actually will happen to the core, i.e., you will induce somehow voltage in the core as well. So some voltage is induced inside the core. Yeah. Okay. But the effect is slightly different. In the coil is straightforward. You've got a plus and minus, so you know how the current will flow inside the coil. But in the core, the voltage is induced somehow, so the current that flowing inside the core is more like an eddy in a river. Eddy in a river is just like this picture here. Yeah, can you see? Yeah. So the water in this case and the surface will flowing in this kind of pattern. So similarly, the current in the ferromagnetic core is flowing in that sort of pattern as well. So like what I have drawn here as illustration. Okay, and then because there is a current flowing in this conductive material that will have resistance, you got current, resistance. This is a recipe for conductive losses. Remember, P is equal to I to the resistance in the core, and this will basically turns into heat. Yeah? So you can feel that the core will get warmer and warmer. Okay, right. So these eddy currents are flowing in resistive materials, so energy is dissipated, which lead into heating the iron core. The amount of energy lost due to eddy current depends on first the size of the current swirls, yeah, this is the eddies, and then the resistivity of the material. Yeah, the size basically referring to this cross-section area. So if you want to reduce this or minimize this eddy current loss, we can achieve it by two different ways. Yeah, either we make the size smaller, or you increase the resistivity of the material. If the resistivity is increased, the current will be reduced, and as the current is reduced, the loss will be reduced as well. Okay, so how do you reduce the size of the current? You reduce the size of the current by breaking up. By breaking up the ferromagnetic core into parallel laminations. This is how you reduce the size of the current source. and you can see it on the illustration here. Yeah. So if you just use a single chunk, yeah, one single block for the core, this is what you get. This is the size of the eddy currents. But if you split, for example, the core into two like this, so you got two layers, yeah, the second drawing, then the size will be smaller. Okay, and then if you then split it into even thinner layers, yeah, stack of laminations like this, then the size of the eddy currents will be even smaller. And by doing this, then you basically minimize the eddy current loss. You'll be able to see if you got a what we call a transformer. Maybe you have a transformer at home, or you open up a laptop charger, for example. Normally inside it you'll find a transformer. Then the core will be made up of these stacks of laminations like this. And again, the idea is to reduce the eddy current loss. Okay, and the second method, you're adding silicon to the steel core to increase the resistivity. Silicon is not conductive, so but if you mix the core, yeah, the steel core with the silicon, then the resistivity will be increased. And again, by having higher R, you will reduce the I. And by doing this, you will reduce the eddy current losses. Okay, so these are the two. Right. Okay, I think that's all. On the two losses, and yeah, so the core losses again will be the sum of this, yeah, P of the eddy current plus the P resistance losses. Okay. Right. Okay. That's all. Some introduction of the core losses that we have. Later on, when we talk about the what we call the electrical machines, we will have some other losses. Yeah? The friction losses, which is mechanical, and also some electrical losses. Yeah, for example, because of the resistance in the wires or the coil. Right. Okay. Any question? Okay, 33. I think we have just enough time to finish. Any question before we move on to the next topic?
No, sir.
It's okay. Right. Okay. Yeah. Okay. No questions. Okay. Let's go to the next topic then. Yeah, again, you can always do revision later on, and then if you have a question later on, you can also write it in the WhatsApp, in our WhatsApp group. Right. So what is the next topic is, it is on powers in AC circuits. Yeah? We need this knowledge later when we discuss or analyze the performance, yeah, like the efficiency of electrical machines. Okay. So when we talk about AC circuits, then the power becomes a bit more complicated. In DC circuit, the power is simply just V times I, yeah? And that's the only type of power, which is also called the true power or real power. But when we discuss or we talk about AC currents or AC circuits, sorry, then the power gets a bit more complicated. Yeah. So there are these three different types of power: the real, reactive, and apparent powers. So what they are? Okay, the instantaneous power, yeah, which is the total power at a given time, is still the product of the instantaneous voltage and the instantaneous current. but the average power supplied to the load is affected by the phase angle. Okay. So if we are talking about the instantaneous power, then it's just again simply just V times I. Yeah, V at that particular time times the I at that particular time. Yeah, but when we talk about this real reactive apparent power later on, the average one, then this all the actual magnitude will be affected by the phase angle between the voltage and the current. Okay, now we are going to consider a scenario, yeah, so that we can explain it in a more detail. So consider a single phase voltage source supplying power to a single phase load Z with the impedance Z angle theta. Okay, so you've got this voltage supply, yeah, AC, sourcing voltage, yeah, and that's the voltage V angle 0, and then this is the load, yeah, with impedance Z angle theta, right? And because it's already a closed loop, current will flow. Then you can calculate the current, which is the voltage divided by the load impedance, yeah, and it's equals to this. You can see the angle of the current is minus theta because the angle of voltage is 0 and the angle of the impedance, load impedance, is theta. Yeah. So 0 minus theta gives you the minus theta. Yeah. That's why we have minus theta as the angle of the current. Okay, the voltage applied to the load is this. Yeah, V of t equals to square root of 2 times V cos omega t, and V is the RMS value, root mean square value of the voltage. And then the resulting current flow, yeah, is this. We've got the difference here in terms of angle because of the angle of the impedance of the load. Okay, now the instantaneous power supplied to the load, you just multiply them together. V of t times I of t. Okay, and should give you this. Yeah, this is again the instantaneous power. And then if you use a trigonometric identity, you can expand this expression, yeah, from there to this. Okay, all this, I mean, yeah, not just that one, but all this. So the instantaneous power, if you look at this, basically consists of two different components. Yeah, first component is here, and this is the second one. Okay, so the first one is this VI cos theta, and the second one is starting with the VI sin theta, blah blah blah. Okay, right. So the first term, yeah, represents the power supplied to the load by component of current that is in phase with voltage. This one here. Yeah, by looking at the angle, you can see that it is in phase with the voltage, but the second term will have a different phase. Yeah. It's 90 degrees out of phase with the voltage. The voltage, you can, this is the voltage. Yeah. So this is the phase of the voltage, omega t. Okay, right. Sorry. Okay, let me just check again. The VI cos theta. This is okay, I need some space to expand this a bit. Yeah. So the first term, VI, oh, sorry, VI cos theta times 1 plus cos 2 omega t. Remember, theta is constant. Yeah, this is the phase angle of the load. Yeah, impedance. So this is a constant. That's all these are constant basically. So Vi, this you can expand it into Vi cos theta plus Vi cos theta cos 2 omega t. Okay, I hope you can read my handwriting. So this is the first term only. Yeah? Remember, this is the first term only. Actually consists of these two. I'll speed up a bit, I think, so we can finish on time. Okay, Vi cos theta is again this will be a constant, while this is actually will be a cosine wave. Yeah. So cosine wave plus a constant, and the magnitude of the cosine wave is the same as this value. Yes, both are Vi cos theta. So what is it? This is actually a cosine function that has a bias. Yeah, it's been shifted up by Vi cos theta, and you can see if you plot it, then you will have this what is drawn in this solid line here. Yeah. So it's a cosine wave that has a bias, yeah, of Vi cos theta, which is the magnitude of it. So this is the bias, if you like. So it's not going across zero like normal. It's not like this, but it has been shifted up by Vi cos theta. And so the function will go towards zero. Yeah, it's close to zero, but then after it's touching zero, it will go up again. So it never goes into negative. Yeah, this is what is this first term representing. Okay, while the second one is just simply a sine function. Yeah. Okay, because in this term that is changing is only time. Yeah, the t, the rest are constant. So when you've got this sine 2 omega t, you know that this is a sine wave. Okay, this Vi sine theta, again, this is just a constant. Yeah? Because it doesn't have t in this term. Only in here we've got t. So again, this is just simply the magnitude of the sine wave, and the sine wave itself is a sine 2 omega t. Okay, and there's no bias here, which means that it will go around 0 point. So if you plot this, you will get the dotted line. So it's a sine wave around 0 point, line. Yeah. Okay, so there are two powers. So this instantaneous powers consist of these two elements. One is the solid line, and the other one is the dotted line. Okay, right. The solid line is always positive, yeah, or zero, and it produces pulses of power instead of a constant value. Yeah, so it's pulses of power. It goes up and down, yeah, like this, and this is actually the real power. Yeah. That will be transmitted from the source to the load. Okay? And the second term goes positive and negative. So if you imagine, it goes positive. When it's positive, it goes from the supply to the load. But when it's negative, it actually goes from the load to back to the supply. So this power is also we call it as the reactive power. Okay? Q. The symbol for it is Q. And again, it's going back and forth from the supply to the load back to the supply. So it's not doing any work. Yeah, it's just, that's why some people also call it useless power, because it's not doing any work. It's different from the real power. The real power, if the load is, for example, a motor, then it will be converted into motion. Yeah, while the reactive power is just transmitted back and forth between the source and the load. So it's not doing anything much. Okay. So the reactive power represents the energy that is first stored and then released, yeah, in the magnetic field when we talk about inductor, or the electric field in capacitor. But again, it's not doing any work. Okay, so we have three difference of powers. Sorry, the last type of power is the apparent power, S. It's the apparent power, which is just the sum of the real power and the reactive power. So S is P plus Q. Later on we'll see in more detail. Okay. So you got three types of power again. P is the real power, and this is the actual power that will do the work. Yeah. If it is motor, then it will do the whatever the motor is doing or working on the doing some motion. Yeah, producing some motion. And the reactive power is the one that is not doing any work. Actually, it just goes back and forth between the source and the load. And the apparent power is the total of this P and Q. And each of these will have a different units. P have the unit of watts. Q is voltage ampere reactive, VAR, and the apparent power just voltage ampere. Okay. Then we have this concept of power triangle. This is very useful for us to do analysis and to remind us as well the direction and how we can use this triangle to help us doing the analysis later on. Okay, in this triangle, oh no, yeah, we've got this triangle. P is always horizontal, Q is perpendicular to perpendicular to P, yeah, the Q, the reactive power, and S is the total, yes, the hypotenuse of this triangle. Okay, and if you use the Pythagoras, then the S squared equals to P squared plus Q squared. Okay, just this equation there. Right, and then this is the angle theta. Okay, so if you have this triangle, then it helps you. For example, you know that cos theta will be P over S. And cos theta, the term of this is also called the power factor. Okay, this bit here. Power factor, yeah. So the ratio of power, real power to the apparent power. The highest value for this is 1, and this will be the ideal, yeah, because the real power will be equal to the apparent power. So all the power will be useful. You don't have the reactive power, which is useless. Okay, the power factor can be leading, yeah, leading or lagging. It depends on how the current is the phase of the current relative to the voltage. If the current is leading, then the power factor is also leading. If the current is lagging, then the power factor is lagging. Yeah. When the power factor is leading, the reactive power is negative. When it's leading, yeah, power factor Q is the reactive power is negative, and the load is capacitive, and the angle of the load will be positive in this way. So be careful when we talk about theta. Theta being the angle of the impedance will be positive here. Okay, and if theta is referring to the angle of the current will be negative. Oh, sorry, the angle of the current will be positive. Current of the angle, the angle of current will be positive. Angle of impedance will be negative. Yeah? This is for the power factor leading. Okay, we'll touch again on this later on. Yeah? But we somehow need to remember this. Okay, how do we know the load is capacitive or load is inductive? Yeah? The term. Sorry, 1250. Can you finish it? Can you bear with me? Just 5 minutes inshallah. So we've got this, I think we call it mnemonic word to help us to remember civil. So civil, you've got C and L. Yeah, C for capacitors, capacitive load, and L is for inductive load. When for the C, you can see that the I comes first, yeah, before V, means that the I is leading. Okay, so when we have capacitive load, the I is leading, yeah, it comes first before V. But for the L, the I comes after V. The I comes after V, which means that the I is lagging, yeah. I don't know, it's a bit too fine, yeah. I don't know how we can still read it. Yeah. Again, for capacitive load, the I is leading, the current is leading. For inductive load, the current is lagging. Okay. So you can see here, for inductive, I is lagging. Yeah. You can see on the table as well. When the load is inductive, the current is lagging. So this is how you can remember it. Okay. And then when the current is lagging, the power factor is also lagging. Okay, so hopefully that can help you to remember. And then finally, just one more thing. Yeah. One more slide. Okay, the S, remember, is the total of P and Q, but P and Q have got different angle. Yeah. So if you like, S is equals to P plus IQ. Yeah. Is in the if we assume this to be Argand coordinates, the Q is in the imaginary axis, P is in the real axis. So S is equal to P plus IQ or JQ. Maybe I just J. I maybe confusing with the current. Okay. So S equals to P plus JQ. Yeah, which is this one here. Okay. Another way, S is also equals to V times I conjugate. Yeah, conjugate vector is given by this. Yeah, if you have I equals to I angle beta, then I conjugate is the basically just change the angle into the opposite polarity, yeah, which is I minus beta. That's I conjugate. Yeah, so S equals to V times I conjugate, and then if you then work this out, then you should find that is equal to P plus JQ as well, which is the first one that we've already got from the power triangle. Okay. Yeah, I don't think we have time to look at the example, unfortunately, but I hope you can self-study. Then let me know if you have any. So inshallah we'll continue again on the next session on Monday, inshallah. Right. Just before we dismiss, any question first or any concern?
No, sir.
One. Okay, good. Okay then, yeah. I think we just call it a day now. If you have any question again, you can just type it in the WhatsApp, or you can use the iTalim as well to pass your question to me. Inshallah. Right. Okay. Now let's just close our class today. Thank you very much for your participation in the class. Hopefully, although we have to do it online like this, you can still get a good understanding about what I've tried to explain through these slides. Yeah. Let's now close the session by reciting Suratul Asr and Tasbih Kifarah. Okay, again, thank you very much. Okay, see you again inshallah next time. Assalamualaikum warahmatullahi wabarakatuh. Thanks.
Waalaikumsalam.